Our next speaker is from OneSpin Solutions, another sponsor, gold sponsor, and the speaker is Ashish Darbari, who's the Director of Product Management. Dr. Ashish Darbari leads the product management team at OneSpin, who's been championing formal verification for over 14 years in senior roles at Imagination Technologies, General Motors, ARM and Intel. He holds 7 UK and 2 US patents, has published numerous papers in leading conferences and industrial forums. He is a Fellow of the British Computer Society, Fellow of the IETE, and a Senior Member of ACM and IEEE. Since 2015, he's also a Royal Academy of Engineering Visiting Professor at the University of Southampton. You got time for a day job as well? The title of his talk is Rediscovering Coverage. Rediscovering Coverage. Indeed, the grass is greener on the other side.
Oh, thank you, Mike. Okay, so I picked this title for a reason, and you will see why this is. So, before I go there, the verification loop is something that everybody here in the room would relate to. We start with requirements, and we had a lot of discussion today on requirements-based engineering and systems engineers capturing or not capturing requirements. And you go to verification plan, and you build a test bench. Then you run the test bench, do your debug, and then you ask the all important question, sign off. Can I ship my design off? So why grass is greener on the other side? So I'll give you a verification engineer's perspective on this. So back in the days when I was not working for EDA, so I'm in my new role in EDA, I've been a long-standing user of EDA tools and formal verification tools in particular. I had a combination of techniques which I would use in my daily life to do the sign-off. So they would start with peer reviews, structural coverage metrics, functional cover properties, and what the formal tools call witness runs, detect over constraints, would go and then plant some bugs in a handcrafted manner, something on the lines of fuzz testing, what was being discussed earlier in the security track. And then, if there's enough time, would exercise mutation-based tools. So what's changed now? So what's changed is that, unfortunately, I wasn't a OneSpin user before, so I wasn't aware about what OneSpin's coverage offering was. And in the last few months that I have been with OneSpin, I started looking at what the coverage solution is that OneSpin provides, and started to look at the relevance of what it does and what it doesn't. Some of the questions that I started to ask is the coverage solution answering the correct question? Is it generating the correct metrics? Is it giving me the quantitative view? Is it giving me anything on the quality side? How are metrics linked to the quality of verification? What is the cost of running coverage analysis versus returns? And how much time, how much delta do I have to spend? So before I dive deep into what the coverage story is, the OneSpin's coverage story actually falls into two different camps, two different packages that we have. One is around product called Quantify, and the other is the gap-free analysis. So I won't go into the details of gap-free analysis, but it all starts from the motivation of tracking progress. And what we are trying to say here is that as much as the structural coverage is important, functional coverage is equally important. And what is even more important is to be able to have a view of both of these metrics in the same visibility window, so you can actually track both of these things down. So we start from auto checks, which we have a product called DB-Inspect, where you can run toggle check, branch, condition coverage, FSM coverage, and all of the line, statement, and the block coverage. But what is also happening at the same time is we have this product called Quantify, which is one push button command in the tool, which if you were to run, can give you lots of useful coverage information and can reveal you incompleteness issues around your functional verification test bench. This is the bit that really is exciting for me, because I have struggled to get these answers before. So if you don't measure, you don't know, right? So have I written enough stimuli to cover all requirements? Which part of the design has been exercised by my assertions of cover? Have I written good quality checkers? Which parts of the design has been checked by my checkers? Are all specified functions implemented? Are all specified functions verified? So what we have is, as I said, two different solutions. One is quantify and the other is the gap-free. And today's talk is focused more on quantify. So what is quantify solution? So what it does is it actually gives you an indication on quantity as well as the quality. So it takes as input a hardware design and your formal test bench. And you type a single command and you get a metric-driven sign-off report as output. And I'll show you what this report looks like and what it gives you. And that's all there is to this. There is no complicated setup. There is no overhead of going through lots of hassles. And from what you get as a result, it's actually pretty good. So the two aspects of the solution is the structural coverage, the quantitative side, which is which bits of my design signals have been reached. And the other very useful aspect of this story is, have I observed all of my key design signals? And if not, then what exactly is going on in my test environment? So that's the question that is answered by observation coverage, and the control coverage answers the question on which signals have been reached. So one is the reachability analysis, other is the observation analysis. The other dimension to the solution, which is the assertion coverage, which actually tells you which assertions were sensitive to which parts of the design. And actually, if you were missing a check, the coverage tool will tell you that you're missing some checks. You can go and then add those checks, and you not only increase your coverage goals hitting more towards 100%, but you also end up finding more bugs. So actually, this is the key here, that actually you are able to see the information about metrics and the quality, the quantity and the quality, both in the same dashboard view. So to cut it short, the control coverage problem is about which parts of my design under verification has been exercised, and informal because there is no stimulus testing to be done, there is no stimulus writing to be done. Formal applies all possible stimulus which is allowed by the constraints. This problem about have I written enough stimuli is about detecting over constraints in your design and verification test bench. And the coverage, which is around observation, this is the bit that actually allows you to figure out whether you've got good quality checks. So it's not just good enough to find out that you have a missing check, but actually if you do go and then write a missing check and the tool says, oh yeah, you are better off than you were before, but it also then finds other areas of the design which may not have been exercised or observed even after you went and added the check. So it gives you that indicator as well. So this is the key thing about observation coverage. And this is, and by actually being able to highlight which parts of the design have still not been observed, it gives you an indication of incompleteness in your verification. So you have a test plan, you have a stimulus generation apparatus, or in the formal's case, it's controlled by constraints, as I said, you have checkers as assertions, and the coverage metrics are intending to give you a report. So the question we are asking is, how much of my DUV is verified? When am I done? So how good are my test vectors? How good are my checkers and assertions? And the two dimensions that I'm showing here is the control and the observation coverage. So this gives you the structural coverage view. And as I said, there is another dimension to this coverage solution, which is how much of the assertions actually are being sensitized to the design. And if you have missing quality or missing checks, then you add more checks and you make judgments on quality. So some of the aspects of the report might be easier to see it in a split way, and I'll show you how it looks like in a dashboard. So we are able to indicate which bits of the design are dead, so they're not reachable at all. This could be independent of constraints. Which bits of the design are reached, so clearly there is something useful happening in the design. Which bits are not reached because of constraints in your design, in your verification test bench. So it gives you three different pieces of information in the controllability side. And then if you are able to reach something but not necessarily observe that, or if you don't actually reach and you don't observe at all, then it says it's uncovered. So if you take a design and you just run quantify on this, it will tell you all of the design is uncovered because you've got no check right now, there's no test bench, it tells you nothing is there for me to do. So your design is all red. And when you do have reachability and you have observability for all design signals, then you get 100% coverage, which is marked by covered in green. The other bits that are also very interesting to know, especially if you are into designing low power and highly optimized designs, not to have lots of spurious area, is to be able to find which bits of your code is redundant, which bits of the code can be excluded because it's not going to be used anywhere. You could have verification code, which you don't necessarily need to do a lot of analysis on. You could exclude that. And then you could have manual waivers, and you can say, I want to just exclude these things. So we provide the feature in reporting, and you can tag different things. Right, so this is how the structural view looks like in the Quantify's dashboard. We provide color annotations, and if you see the maroon and the black and the red, that's indicating there's a verification hole. So the two key points to remember is if it's unreachable, it implies it will be unobservable because you can't observe it because that line of code is not even activated. If it is observable, then by implication it has to be reachable. Right, so this is how the dashboard view would look like if you run the tool. So it will give you all of your metrics in the structural coverage at the very top. Then there are sections where it will display what bits of the code are excluded. It then provides the window on assertion coverage. And if you start having interesting bugs in your design or checks that fail the vacuity check, or they have, or you have other such things that can actually make the antecedent of the assertion fail, then you will start getting that information here in the assertion coverage window. So these three elements of the dashboard need to be looked at at the same time to be able to get a sense of how good your quantity and quality is. But it's nice because it all happens literally by just typing one command, right? There's really no setup or anything required here. So if you had a piece of design where you had run some quantify, it will start telling you which bits are covered, which bits are your verification holes, which bits are constraint code, and where is the dead code. So in summary, it analyzes controllability and observability, as I said, and you can look at it and you can figure out why something is wrong in your test bench or in the design or both. So I just wanted to share some insights. So some of our customers who have used this and who are sort of very safety aware in some sense because they're supplying to the automotive ecosystem, they have used the tool, and what we have learned from some of the customer presentations in November 2013 DV Club is that actually the runtime performance is great. And this is a data that is available from Mike's website. You can take a look at it. It's a unique patented technology. It's much more accurate than cone of influence analysis. And as I said, it requires a single command. If you were interested to know how this would be useful for functional safety qualification, and there is also a work done by one of our customers that is recorded in the STAC 2014 paper, and this paper will show you how a quantitative assessment of formal verification environment was addressed by using observation coverage. Right, so what was the problem before, and what is it that we are offering in OneSpin is superior to something else? And so for a long time I've heard other formal tool vendors tell me that you could use cone of influence coverage. And the problem with cone of influence coverage is that depending on the assertion that you write, the tool then does a structural and a semantic cone of influence analysis under the hood and can decide to include or not include certain parts of the design for analysis. So this can actually be quite misleading. And to give you an example why this is so, if you look at this property, right, this is a FIFO design where we are trying to find out that if the FIFO was originally empty and then on a write enable we wrote some data WR data, value dat was written on WR data, then when the read was requested, what you really want to check is whether you got the value that you wrote. But incidentally, there is a little mistake in this property, and it also says, oh, by the way, the assertion could also be true if the FIFO was either empty or it was not full. And the problem is that it could be not full from the time you start filling it up until the time it gets full. So if you ran this property, the cone of influence analysis would tell you, oh wow, this is great, you know, you've got this covered. And the problem really is this line of code here that is giving you a very optimistic result. So if you ran quantify, it will give you much less coverage and the precise coverage. So actually, if you do the analysis, it's actually much worse because there is a bug in the design that is not getting caught by your assert. That's even worse, right? So if you get a COI coverage of 100%, you are now left thinking, I'm done. I can sign it off. But actually, there was a bug that you couldn't have caught if you went with that coverage information. So this is why we hold this view that actually the cone of influence coverage is not necessarily the best way to address the coverage story. The other problem I have is the proof code coverage. So formal tools actually employ a lot of abstraction automatically under the hood, and they could actually not use certain bits of the code because they may think it's not necessary. So therefore, it will not be reported to you as having been exercised when you are checking assertion A. So what's not covered is what the proof engine did not need, right? So the problem is if you are using a smarter proof engine, which you would like to because you would like conversions on your proofs, you will get lower coverage. Oops, I don't know what I did. Let's see if I could do it again. So our view is that actually the cone of influence coverage and the proof core coverage are not the right metrics if you were linked into safety, functional safety for hardware. Mutation coverage is an interesting one. So there are vendors who are providing mutation coverage based solutions. It's actually a good way forward, but the problem actually we see is that it's quite a high runtime, and by default you have one fault at a time, or you could start injecting multiple faults. But the main problem here is if you're replacing a line in the code that B is getting assigned to A by a mutation, it could actually introduce vacuity, which may or may not be necessary for you to get the right confidence. And the other thing is mutation is applied on the actual line of RTL code, and you require iterative compiles and runs. So this basically will add more time. So if you wanted to actually cover all locations, all types of fault models, then there is more work required. But it's certainly qualified for safety. What we believe, if you get to use our tool, then basically you get the best combination of safety, qualification, and runtime overhead. So what we do is we don't actually mutate the line of the RTL. We compile the whole RTL, and then we actually work with a model of the RTL inside the tool. And we replace the assignment statements in RTL, not by specific mutations, but by introducing free variables that allows a bigger class of behaviors to be exercised when the tool is rerun to check the quality. So what we have done is just the right level of abstraction to get the observability outcome. So in this sense, what we are doing might appear as similar to you, to the mutation-based stuff, but in terms of performance and in terms of actual quality of results, we produce different outcomes. This is something that if you were a user of other tools, you might want to actually appreciate this. So in summary, what I have introduced today to you is a coverage solution that is targeting assertion-based verification, formal verification using ABV. I learned from one particular person today that he's designing his chips without using formal. My advice would be consider doing it, as it would be useful for you. So if you don't use formal, perhaps you should, and if you use a formal tool and don't use ours, then it's worth giving it a look and finding out what it does. Probably will solve some of your coverage woes. So what we are saying here is that, and this is me having looked at and having the benefit of having played with other tools in the market, I truly believe OneSpin is the only vendor in the market that provides a complete end-to-end coverage solution. So we not only provide you the structural coverage, we provide you the functional coverage aspect as well through Quantify. And gap-free, which I haven't covered today, has been a long-standing technology in the OneSpin thing, which will actually allow you to do high-quality requirements-based verification. So it's aptly suited to addressing coverage challenges for automotive and functional safety. However, there are some interesting next steps because we don't make simulators, and a lot of our customers use simulation and formal. The next few questions that we need to look at is how do we integrate the formal assertion coverage results from our tool into user verification plans, and how do we actually provide hooks into cross-vendor integration. And in general, this would allow verification engineers who are using simulation and formal to be able to have a unified view of coverage linked into the plan. So those are next steps, and hopefully if we can get some progress, we'll let you know in due course.
Thank you, Ashish. Thank you. Thank you, Ashish. Thank you. Any questions, Ashish? Hi.
Hi, Ashish. It's good to see you toning down after you've turned on to the other side. So the question is, do you get the same set of information on bounded proofs?
Yes. So there is we have a feature where we can say use bounded proofs, and then Quantify would give you the rate on bounded proofs. When we talk to customers, it's not clear what value bounded proofs are actually giving to you. So we could actually show you which lines of the code were exercised or which ones were observed. And if you find that useful, that's fine. But for us, a bounded proof is a bounded proof. Your job's not finished. So I guess that's the view that we have. So we are not going to tell you how many cycles it took or how many, what was the cone of influence result, because all of this is not the right way of solving that problem. But yes, there is a switch that you can use.
Okay. Okay, well, thank you very much, Ashish. Thank you.
Thanks, Mike.
And